Here are a pair of problems on rotation taken from Tipler and Mosca's Physics for Scientists and Engineers. So, examples that aren't from the textbook we're using, so all of those examples are still good for you. They're added bonus things. So, a uniform, thin, I should spell check. Thin rod of length L and mass m is pivoted at one end. It is held horizontal and released. Effects due to friction and air resistance are negligible. Find the angular acceleration of the rod immediately following its release and the magnitude of the force F exerted on the rod by the pivot at this instant. So, I have here some forces, and I'm asking for an acceleration, so this makes me think Newton's second law. And I don't want to write in that color. Very particular about these things. So, I know, because I practiced translation-wise, it's F equals ma. So, because I know I switch all these things, I know here that torque is equal to I alpha. So, I want alpha, which means I need both of these. I need the torque, and I need to find I. Now, let's do the torque first. Whenever we're doing this, either of these, we need to identify an axis. This is going to be rotating about an axis through this pivot. So if that's the axis about which I am rotating, I have two options for torque. I can have a torque from F, and I can have a torque from FG. Now if I look at this, I'm going to have that it is, so it's R times F times sine theta. Same deal here. Say R to F and R to G, where those are the distances to where those forces are being applied. So the trick with this is, we're doing this RF, F is being applied at the axis. So this is 0, which means that it cannot supply a torque. This is an important point, a useful point. If I push at the axis, I'm going to translate the object. I'm not going to rotate the object. So this is the only torque I have to worry about. So this is of length L, the whole thing. So, nope, getting ahead of myself. So if the whole thing is length L, then gravity is going to be supplied at the center of mass. So the distance is going to be L over 2. The weight will just be mg. And if I look at this, R, this vector that goes from the axis to the point of application of the force, that's what we had called RG. The angle between that and the applied force, the weight, is 90 degrees, so sine theta is just 1. So this is going to be my net torque. It's not too bad. Now, it's not enough to know net torque. I also need to know I. So there are two ways to do this. One, look in a table. If we look in a table, and I really probably should have had that table open already so that I'm not going here. It's something like, I want to say 1/12 mr squared, but that's been, yeah, so we look at the table, we see an example for a thin rod about perpendicular, nope, that's not what yeah, we don't want that. So if we do it this way, we have, it's going to rotate downwards. Oh, yeah, that's fine. So a thin rod, could get a thin rod about a perpendicular line through its center. But we're not rotating about a line through its center, we're rotating along a line out on the side of it. So we could have to do then the parallel axis theorem, where we would say that the moment that we want is the moment from the center of mass plus this translating term mh squared. Which, so the center of mass, we look at the table, we see is 1/12 ml squared if it spins about an axis through the center. And since it's shifting by L over 2, we would have to add this term. So we have 1/12 ml squared plus 1/4 ml squared. 1/12 is 3/4 is, well, no. 1/4 is 3/12, so it's 4/12, so it's a third. ml squared would be our moment of inertia. Or we can do it by calculus. If we do it by calculus, we're going to say that we're going to integrate dm r squared. dm for a uniform rod, well, our idea for this is that the little mass over the little length is the total mass over the total length if it's uniform. So dm would look like m over L dx r squared. R in this case will be x squared. We're going to integrate from 0 to L. So if we carry out this integral, m over L comes out. I integrate x squared dx. I get 1/3 x cubed from 0 to L, which would be, shockingly enough, 1/3 m L squared. Good thing they both equal the same thing. That would have been really annoying if they didn't. So, if I know the torque and I know the rotational inertia, I can calculate alpha. I know that alpha is then going to be the torque by the rotational inertia, or let's see, mgl over 2, and then we have a third ml squared, which would be 3gl over 2, if I do my math right. If anybody wants to check that, I would be most graciously appreciative, actually, I should say. That would be how English works for most people. Nope. That's how you do division. Alright, so that takes care of A for us. Now, the question we next have to ask is, how do we find the magnitude of the force F exerted by the rod? If we're going back now to forces, we need to turn this back into a translational problem. So, if we scroll all the way over, Newton's second law traditionally looks like F net equals ma, right? If I were to compress this, the forces acting on it would be Fg and F. And this is and the center of mass is accelerating, and the question is, what is the acceleration now of the center of mass? The secret of this is we've always looked at the acceleration of the center of mass, we've just never cared about the acceleration of any other part. Well, we know that the linear acceleration looks like the radius times the angular acceleration. So the radius of the center of mass from the axis is L over 2. And we just said that this is 3g over 2L, the angular acceleration. So the linear acceleration should be 3g over 4. Which means that Fg minus F should equal 3mg. I'm using a capital M, sorry. Over 4. So mg minus 3mg over 4 equals F. Or F is equal to 1/4 mg. So that is one nice kind of then dynamics problem with this. We're dealing with forces. We're looking at rotational inertia, we're looking at torques. Let us look at a second example. It's a pulley problem, everyone's favorite kind of problem in the world. So, two blocks are connected by a string that passes over a pulley of radius r and moment of inertia I. The block of mass m1 slides on a frictionless horizontal surface. The block of mass m2 is suspended from the string. Find the acceleration a of the blocks and the tensions in the string. We should point out there do have to be tensions, two different ones, because the pulley has to spin. For the pulley to spin, there must be two different torques on it. So this can be a little tricky to think of, but remember, a tension, when you have a rope, acts inward from both sides. So that means that this tension is trying to spin the pulley in a counterclockwise direction. And this tension is trying to spin it in a clockwise direction. So the net torque on the pulley looks like the difference of the torques supplied by the tension. So let's start there. Let's look at the pulley. And so here we have that the net torque is equal to I alpha again. Now, the pulley we want to think of as a disk. And again, this is something we can consult in a table to get I. So I for a disk is going to be 1/2 mr squared. I say as though I've memorized this and I'm totally confident, while in actuality I'm flipping back to a table to make sure that I'm not a crazy person. Hey, look at that solid cylinder about axis. Woo! Alright. The net torque, in this case, is going to look like T2. We know that the pulley's radius is R. And it's going to be acting, so we can think of this as connected in such a way as to make it perpendicular. Just kind of go with it. Minus T1R. And so we get that alpha must then be T2 minus T1 twice this over MR. Yes? Yes. So that's useful. It's doubly useful because this must have a linear acceleration that matches everything else. So then A must be R alpha, must be twice the tensions, twice the difference of the tensions over M. Which you'll note is an acceleration because it's a force divided by a mass. Alright. So that would help if I didn't have to also find the tensions, because I don't have a clue what the tensions are. Well, now let's take a look again from a force problem. So if we want the tensions, and we have this acceleration, then we know information, that we can look at from a force perspective. So we know M2 has its weight pulling it down, and the tension pulling it up. T2 specifically. Now be very careful here. This was a point of great contention for a lot of people. When looking at these Atwood machine problems, you have to be very cautious about what you're considering the acceleration and what forces are actually in play. It is not just gravity acting on the hanging mass. So, looking again at Newton's second law, F net equals ma, we would have Fg2 specifically minus T2 equals m2a. So, T2 would equal m2g minus a. Would be more helpful if we knew what that was, but one thing at a time. I really should probably solve these in advance, but it's much more exciting this way. Frictionless, so this is the only thing that we have going on here, is just T1 acting on M1. So then we simply have that T1 is equal to M1A. So A is equal to T1 over M1. Alright, so if we want to put these in terms of stuff, let's see. What is going to be the cleverest way to do this? So I have three equations and I have three unknowns, T1, T2, and A. So A is equal to 2 over M, T2 minus T1, T2 is equal to M2 times G minus A, and T1 is equal to M1 times A. So let's try this out. Let's calculate T2 minus T1. So it's M2 G minus A minus M1A. We'll plug that on into here. So A is equal to 2 over M. Oh, need a lot more brackets than this. M2 G minus A minus M1A. Now I just need to isolate A because everything else is totally good. And this is totally doable, I'm sure. 2 over M. M2G minus M2A minus M1A I guess I need to distribute that, so I get 2m2, nope, not mg, that's confusing, m2g over m minus 2a over m1 plus m2. I think I'm okay with that. So then add that to both sides, so a plus 2 over m, a, m1 plus m2. I haven't done anything at least that is, you know, going to be terrible from a unit perspective at the moment. As I go through this, you know, I'm trying to make sure I'm not making horrible mistakes. You know, it's not easy to tell if you've made a calculation error in the middle of a stream of consciousness sort of thing. Clearly there's a lot of algebra just going on here, where I'm not entirely certain if I've made a mistake, because quite frankly this feels like a lot more algebra than it needs to be, which makes me wonder if perhaps I have screwed something up. But, you know, distribute this. Oh, no, this actually looks kind of reasonable now. So, why am I okay with this? I'm okay with this because if m2 is... Nope, that's dangerous. Oh yeah, if m2 is 0, it doesn't accelerate. That's great. If m1 is 0, it's basically in free fall for a small pulley. And for a big pulley, it looks like it's attached to something. I think that's viable. So I go and look and see if I have a solution or something by which I could compare to and, like, know if I've made horrifying mistakes. Hey! Ooh, what? Oh, yeah, hey, that's a mass. Turns out the solution didn't expect you to know that the rotational inertia of a disk was 1/2 mr squared. Which maybe they didn't tell you it was that. No. That's cool. What else did I have to do? Oh, well, whatever. If I know what A is, then I can plug into the other ones. They are similarly, like, bizarre looking. So, moral of the story. You need to be able to move back and forth between rotation and translation problems. The information is very similar in both cases, so you need to be conversant in switching between particularly torques and forces, and angular accelerations and linear accelerations. It's that factor of R and the directionality that'll catch you. Hopefully this was a nice kind of starter point. Good luck.